So hello everyone, welcome back to another particular lecture series of our reagent chemistry lecture. So this is our class 7. So in our previous discussion, we are talking about the superhydrate and selectrides. So here today we will discuss about some more nucleophilic reagent, which is much more stronger than those reagent, that is the zinc borohydrate and lithium aluminum hydrate. So first let's talk about the zinc borohydrate. That zinc borohydrate is a stronger reducing agent than NaBH4, lithium borohydrate and selectrides. Okay, and it is also a moisture sensitive reducing agent and stereoselective. Also, it will reduce the carbonyl ester and acid group. And also the important feature of this particular zinc borohydrate, it selectively reduces aldehyde in presence of a ketone, and it is also conjugated aldehyde is reduced, and the reaction mixture, that aprotic solvent has been used, that DCM, DMF, THF, this type of aprotic solvent has been used, and uh, acyclic conformer is more reduced than cyclic system. And when if it is an isolated double bond presence such as this type of thing, then hydroboration observed. Okay, so what should be the reaction? Reaction is if it is an acid moiety, that is benzoic acid, and benzoic acid react with the zinc borohydrate in presence of aprotic solvent THF to getting their corresponding alcohol. And the structure of this particular zinc borohydrate is this. Now let us talk about the chemoselectivity. Like uh, as I already discussed, that if the particular starting material contain both the aldehyde and ketone group, then zinc borohydrate is actually selectively reduce the aldehyde group and leaving the ketone group intact. Okay, so also here you can see that this is our acid moiety and this is our isolated double bond. So in presence of zinc borohydrate, it can reduce both. Like here, it will go via hydrate transfer reagent and to form this type of primary alcohol. Whereas this particular isolated double bond, it is the hydroboration takes place where the anti-Markovnikov addition takes place to get this type of compound. Now let's talk about the regioselectivity. As I already discussed in the previous slide, that acyclic is more reduced than cyclic system. So here you can find that is a both the carbonyl compound, where this particular is the acyclic ketone and this is a cyclic ketone. Now zinc borohydrate is actually reduce this acyclic ketone more or selectively over the cyclic ketone. So this is the overall summary of the zinc borohydrate. Now let us talking about the very interesting reducing agent. This is the lithium aluminum hydrate or LiAlH. In physical property, it is grayish in color and it is completely non-selective reagent for hydrate transfer reduction. Like all the group, carbonyl, esters, then carboxylic acid, amide, all the groups are actually reduced by using lithium aluminum hydrate, and also many other functional group has reduced to or eliminate, and reaction with acidic proton generate hydrogen, and reaction condition is very harsh, minus 78 degree temperature, and ether solvent is required for this particular reaction because lithium aluminum hydrate is pyrophoric in nature, so it tends to catch fire in presence of air and moisture. That's why the reaction condition is very harsh, and it will reduce everything except double bonds. Okay, so let us talk about the mechanism. Mechanism is as similar as the sodium borohydride. Like here, that first the lithium got coordinate with this particular carbonyl oxygen. So the arrow will be in opposite direction. So the lithium get coordinate with this particular oxygen to increase the electrophilicity of this particular carbonyl's carbon center, and then this particular hydrides is actually attacks to generate this type of intermediate, and then on also you can find that three different hydrogen is there to generate the corresponding hydride. So after doing workup, so 1 mole of lithium aluminum hydrate generate 4 mole of hydrate. So that means 1 mole of lithium aluminum hydrate will able to reduce 4 mole of carbonyl compound or something this, and this is the byproduct. And it is the mechanism is purely similar to the NaBH4 based reduction. So whereas the one of the hydride is come from the reagent and of the hydride is come from the solvent itself. Now you can find that very interesting trend from the class where we are starting the reducing agent, nucleophilic reducing agent. So as we go down from sodium borohydride to lithium borohydride, then you can say the reactivity is increases by many fold, and also the selectivity is also decreasing. Like in NaBH4, it is specialized to reduce the carbonyl compounds, but in the case of lithium aluminum hydride, it can reduce everything. So why did it so? So there is a basically two reason is there with this particular problem. So the reason behind this trend is, one is the bond polarity and the second one is the charge density of the counter ion. So first you can see that between the BH and aluminium H. So what happened that this particular bond is more polar in nature over the BH bond, and since this particular bond is more polar, that means the hydride generated from this particular bond is actually much more stronger or much more nucleophilic in nature than this particular BH generated hydride, BH bond generated hydride, and that's why actually the groups contains the aluminum hydrides are more reactive. Just here is a lithium borohydride and lithium aluminum hydride. Both are same counter ion, that is a lithium. But since it is the BH is there and is the ALH is there, that's why lithium aluminum hydride is more reactive than lithium borohydride. And the second thing is the charge density of the counter ion. The charge density of the counter ion says that the more charge in the particular ion, that means the more charge density, obviously. Okay, so that's why the zinc having a +2, that means it has the higher charge density. Now between sodium and lithium, both are having +1 charge, and you can know that between lithium and sodium, lithium have a smaller radius, and due to the smaller radius, the charge density of the lithium is much higher over sodium, and that's why actually the trend continues that the sodium borohydride getting the lesser reactive, and the lithium borohydride is the more reactive than sodium borohydride, and zinc borohydride is much more reactive over these two because of the charge density. And the lithium aluminum hydride is the more ultimate stronger reducing agent because it has the ALH bond, the bond polarity, it will be highest bond polarity over these three, as well as there is the good amount of charge density, and that's why this two factor actually helps lithium aluminum hydride to be the best or the strongest nucleophilic reducing agent. Okay, so now let us talk about the lithium aluminum hydride based reactions. But before that, we're talking about a little bit of selectivity. Like if you have this type of compound where it has several functional groups. Now, if we want to target any kind of one specific group, like if you want to reduce only the carbonyl part of this particular group and keep this two particular other functional group is untouched, then you can use sodium borohydride. Sodium borohydride is selectively reduce the carbonyl part only. Now, if you want to reduce the ester part only, then you can use the lithium borohydride. The lithium borohydride is reduced preferably esters, and these two getting untouched. However, that some time that this particular carbonyl group is also reduced, but in major amount of you can get this type of compound. And if you don't want any kind of selectivity in your reaction, like if you want that every group present in this particular starting material got reduced, then simply use lithium aluminum hydride and you will get this type of compound, like all of the functional group has been reduced. Now let us talk about the lithium aluminum hydride based reactions. So here it is a lithium aluminum hydride. Now lithium aluminum hydride react with the azides, that is the RN3, to getting the amine. Similarly, it will react with the acid chloride to generate the corresponding alcohol. It will react with the ketone to getting corresponding secondary alcohol. It attacks or it reacts with the aldehyde to generate the primary alcohol. Similarly, it reduces ester to their corresponding alcohols. Carboxylic acid is also getting reduced by the lithium aluminum hydride to generate this particular alcohol. Also, the amide and cyano also reduce to their corresponding amines. And if it is an epoxide, then it will attack from the less hindered side. The hydride attacks comes from the less hindered side, and it will generate secondary alcohol. So you can find here that lithium aluminum hydride is basically reducing everything except double bonds. Now let us talking about similar kind of reducing agent, that is a red aluminium. Red aluminium, the full form is the sodium methoxy aluminium hydride, or it can be termed as SMEH or red aluminium. And the structure of this particular compound is this. This shows the similar reactivity of lithium aluminum hydride. However, it will show some different reactivity also that I will discuss in the next slide. So first, let us talking about some information regarding the red aluminium. So first, it is a moisture sensitive reagent, and the second is that it is shown the similar reactivity like lithium aluminum hydride, and it has longer shelf life, and it is thermally stable up to 200 degrees centigrade. And since it is a replace the lithium to sodium, and that's actually makes the shelf life of this particular reagent is much higher, and also not harsh condition is required while using red aluminium hydride. And this is the much more advantage of using red aluminium instead of using lithium aluminum hydride. So let us understand that what kind of unique reactivity shown this particular red aluminium. So red aluminium show similar reactivity like lithium aluminum hydride. However, it shows some more unique reactivity than lithium aluminum hydride, such as that reductive cleavage of ether. Like here you can cite that OBN, like if you attend the protection deprotection class, then you can find that OBN is something this. Now this is nothing but ether. Like in presence of red aluminium in xylene, in reflux condition, this particular bond actually cleaves, and it will reductive cleavage of ether has been takes place to generate this type of alcohol. Also, red aluminium is useful reagent to debenzylation and dearylation of aryl benzene and aryl ethers that are already discussed here. Also, it can do selectively reduction. Here you can find that alpha beta unsaturation is there. Okay, in presence of this red aluminium in reflux condition, you can selectively reduce this particular double bond. Okay, so this is the unique reactivity that a lithium aluminum hydride can't do. And also it will do a stereo selective epoxide opening, like when unsymmetrical epoxide are there, then the hydride attacks are preferably in the less substituted site to give the highly substituted alcohol as the major product. Like here you can find that between this particular center, depending upon the R group, this is the less hindered. So the hydride attacks from here, and this particular bond goes up and to generate this as a product, and the stereochemistry will based on the reactivity. Similarly here also, this is the less hindered side, so it will transfer the hydride from here and not here, and it goes down to get our this type of compounds. Also, in lithium aluminum hydride, it can't react with the double bond and triple bonds, but in the case of red aluminium, it will react with the triple bonds also, and also stereoselective part. Like if you have this type of system, this type of triple bond system, then if you add 4 equivalent of red aluminum hydride or 4 equivalent of SMEAH, then you can find that a trans product is the major one. But if you increase the amount of SMEAH, that is the 8 equivalent or the higher equivalent, then cis product is observed. And this is the stereoselective reaction. And this is because of the particular reason that this particular oxygen actually chelate with the Al present there, and it actually felicitate the reaction condition. Example, here you can find this particular reaction. Okay, so what happened that here you can see that 1.2 equivalent of SMEH has been used. That means the lower amount, and that since it is a lower amount of SMEH used, that means the trans product has been formed. So the mechanistic pathway is that particular Al is actually chelate with this particular oxygen to direct the hydrate transfer pathway, and due to the direction of hydrate transfer pathway, this hydrate transfer from here and this particular bond goes up to getting our trans product. over cis. So let us talk about the summary of our all nucleophilic reduction agent, and this is the master slide of our whole lectures from lecture uh, 3 to lecture 8. Okay. So first let us talking about the reducing agent. NaBH4, NaBH4 imine reduction has been possible. Acid chloride has been reduction possible. Aldehyde reduction possible. Ketone is also possible in room temperature or higher temperature, but in lower temperature ketone is not possible. Ester is usually not reduced by the NaBH4 in standard condition, but if you increase the amount of NaBH4, this is 5 equivalent or 6 equivalent, then it can reduce the ester also, but it is a very harsh condition is required, so we are not dealing with the ester reduction by using NaBH4. And acid and amide are not reduced by NaBH4. Now, if we call about LiAlH reagent is actually reduced still ketone, but it will not reduce ester, acid, and amides. Now, NaBH3CS, the cyanoborohydrate. Cyanoborohydrate is purely pH dependent. In lower pH condition, it actually reduces aldehyde, but ketone is not reduced by this. And in higher pH condition, it will nothing. The aldehyde is also not reduced, but imine and acid chloride has been reduced by the sodium cyanoborohydrate. Now let us talk about the lithium borohydrate. Lithium borohydrate has able or capable to reduce still ester, but it will not capable to reduce acid group and amide group. Zinc borohydrate like zinc BH4 2. So this particular reducing reagent has capable to reduce still acid, but it will not able to reduce amide. And lithium aluminum hydride and red aluminum, it will reduce all the functional group present here. So this is a summary of our nucleophilic reducing agent. So with this, we have to end our nucleophilic reducing agents. In the next class onwards, we are talking about the electrophilic reducing agent such as LiAlH and BH3. So thank you for listening.